guys, today we will be talking about Wilson's theorem. What is Wilson's theorem? Wilson's theorem states that for any prime p minus 1 factorial is congruent to negative 1 mod p. In other words, p minus 1 factorial plus 1 is a multiple of p. So, let's break this down. If we have a prime p, so p could equal 2, 3, 5, 7, etc. And we look at p minus 1 factorial, so p minus 1 could equal 1, 2, 4, or 6, dot dot dot. And we take the factorial of that, which means multiplying all the numbers below it. So p minus 1 factorial could equal 1, 2, 24, 720, so on. Then this number, p minus 1 factorial, is 1 less than a multiple of p. That's what Wilson's theorem states. So let's do an example. For example, if p equals 5, we have p minus 1 factorial equals 4 factorial equals 24. And indeed, 24 equals 1 is equal to 25 minus 1. So it's 1 less than a multiple of 5. And so how do I prove this that works for any p, right? So we want to show this works for p equals 2, 3, 7, and there's an infinite number of primes. So how do we do this? Well, first, we need to talk about something called modular inverses. Modular inverses. What are modular inverses? Well, for any number p, right, prime p, and an integer a between 0, 1, 2, dot dot dot, all the way to p minus 1, there exists, which is what this backward e means, there exists a value b in the range 0, 1, 2, dot dot dot, p minus 1, such that a times b is congruent to 1 mod p, as long as a is not equal to 0, which is kind of important. Well, I mean, like, if a is congruent to 0 mod p, that means that a times b will always be congruent to 0 mod p. For 0 times any number is still 0. So we cannot have it equal to 1 mod p if a equals 0, which is why we say a is not equal to 0. So how do we show this? Well, the important thing is that a is relatively prime to p, meaning that a and p don't share any common factors. Note that 0 and p share a common factor of p, as p divides 0. But since p is prime, I'll draw an arrow, prime, then it's relatively prime. It doesn't share any factors with all of these numbers right here. So if we look at the sequence 0, a, 2a, 3a, dot dot dot, all the way until p minus 1 times a, we want to show right now that this sequence contains all the numbers 0, 1, 2, dot dot dot, p minus 1 in some random order, in some permutation, which just means a rearrangement. So how do we show this? Well, let's assume that for two integers I, j, in the range 0, 1, 2, dot dot dot, p minus 1, with I not equal to j, we will assume, for sake of contradiction, which is what AFSOC stands for, that ai is congruent to aj mod p. By the way, when I say this, I'm talking all of this in mod p. So, like, in other words, like, 3 times 7 is congruent to 1 mod 5. For 7 is congruent to 2 mod 5. And 3 times 2 equals 6, which is 1 plus 5. And so it's 1 more than a multiple of 5. That's what we mean by mod p. So we're working entirely within mod p. And so assume for sake of contradiction that ai is congruent to aj mod p, assuming this condition right here. Then we will have that p must divide a times j minus I. We'll assume that j is greater than I. I'll write this here. J is greater than I. So we know that from the fact that we chose a from these numbers right here, excluding 0, right? Since we chose a from those numbers, we know that p is relatively prime to a. And since p must divide this quantity, a times the quantity j minus I, we know that it implies that p divides j minus I. Or in other words, j is congruent to I mod p. But if we scroll back up, since we chose I and j from this set of numbers, right here, note that no two numbers are congruent mod p, for this contains all the distinct residues mod p, 0, 1, 2, all the way to p minus 1. Note that one number cannot have two remainders when divided by a single number. For example, 21, when divided by 5, leaves a remainder of 1. It doesn't leave a remainder of multiple things, right? So we cannot have this be true without I equals j. So this is not possible, and therefore we will never have ai equal to congruent to aj mod p. This is not possible. So for this sequence right here, we're going to change colors. For this sequence right here, oh, I didn't change colors. For this sequence right here, we will never get the same number twice in a row. And since we're taking mod p, every number is between 0 and p minus 1, we will achieve each number between 0 and p minus 1 exactly once, meaning that it is this sequence in some permutation, right? And note that this sequence always will contain some number that's congruent to 1 mod p, right here, right? Which means that each number has exactly 1 modular inverse mod p, some number that you can multiply by to get to 1 mod p. And so we say that for all a in 1, 2, dot, 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 p minus 1. I left out 0 because we're assuming it's not equal to 0. There exists a b in that same region, 1, 2, dot, 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 p minus 1, such that, that's what s dot t means, such that a times b is congruent to 1 mod p. So now, let's go back to our original problem, Wilson's theorem, right? We want to show that p minus 1 factorial is congruent to negative 1 mod p. So let's scroll down, and let's list out what exactly p minus 1 factorial means. Change your colors again. P minus 1 factorial is equal to 1 times 2 times 3 times 4 times dot 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 times p minus 1, right? And now we want to pair up numbers such that we pair up each number with its modular inverse. For example, if p equals 7, p minus 1 factorial equals 1 times 2 times 3 times 4 times 5 times 6. We can pair up some numbers to get numbers that are congruent to 1 mod 7. For example, we can pair up these two numbers, 3 and 5, because 3 times 5 is equal to 15, which is congruent to 1 mod 7. And similarly, we can pair up 2 and 4, because they multiply to 8, and 8 is 1 more than 7. So a is 1 more than a multiple of 7. It's 1 mod 7. However, you may notice that we have to pair up 1 with itself. For 1 times 1 is congruent to 1 mod 7. It is its own modular inverse. And the same thing is true of 6. 6 times 6 is equal to 35. is equal to 36, sorry. Is equal to 36, which is equivalent to 1 mod 7, for it is 1 plus 35, and 35 is a multiple of 7. So we can pair up almost all the numbers in the middle, besides 1 and 6, with each other to get numbers that multiply to 1 mod 7. Note that we can show that no number besides 1 and 6 multiplies to itself to get a number that's congruent to 1 mod p. The reason for this is because let's say that we have a number a such that it is its own modular inverse. Then we have that a squared is congruent to 1 mod p. In other words, a minus 1 times a plus 1 is congruent to 0 mod p. This is because from this we know that a squared minus 1, subtracting 1 from both sides, is equal to 0 mod p, and we can factor this into this, right? And this means that p divides a minus 1 times a plus 1. Since we know that p is prime, that means that p must either divide this, a minus 1, or this, a plus 1, meaning that a must either be congruent to 1 or negative 1 mod p. In this case, we would only have a equals 1 or 6, which is when it would be its own modular inverse. So then again, we'll scroll back down, and we see that in p minus 1 factorial equals 1 times 2 times 3 times ... times p minus 1, we can pair up almost all the numbers with each other. So we can pair up all these numbers in the middle, excluding p minus 1 and 1, with each other to get pairs that multiply to 1 mod p. So we'll do an example for this. We'll do p equals 13. So p minus 1 factorial equals 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10 times 11 times 12. That's a lot of numbers. So let's see, what can we pair up with what to get numbers that are congruent to 1 mod 13? Well, first of all, we can pair up 2 and 7, because 2 and 7 multiply to 14, and that's 1 more than 13. Also, we can pair up 3 and 9. We can pair 3 and 9 because 3 times 9 is equal to 27, and 27 is 1 more than 26, and 26 is a multiple of 13. We can also pair up other numbers. For example, we could pair up some numbers like, we could pair up 4 and 10, because 4 times 10 is 40, and 40 is 1 more than 39, and 39 is a multiple of 13. Similarly, if we look at the next multiple of 13, which would be 52, 53 is prime, so no two numbers will multiply to that. But the number after that, 65, that's equal to 6 times 11. So we can pair up 6 and 11, and these multiply to 66, which is 1 more than a multiple of 13. And also, we know that we can pair up 5 with 8 too, because 5 times 8 is also 40. And note that we cannot pair 1 or 12 with anything, because, like we said earlier, these two do not multiply to anything else besides themselves to get a number that's 1 mod p. So, since we can break this down, this region, into pairs of numbers that multiply to 1 mod p, I'll write this down, pairs of numbers that multiply to 1 mod p. If we compare this up into numbers that multiply to 1 mod p, and we multiply, I'll write this down, multiply all the pairs. So we multiply 2 times 7 times 3 times 9 times 4 times 10 times 5 times 8 times so on. we multiply all these pairs that we found. This, since each of these is effectively congruent to 1 mod p, this is congruent to 1 mod p too. So the product of all these numbers right here, these multiply to 1 mod p. But if we want to find what p minus 1 factorial is, mod p, we still have to include this 1 and this 12 over on the right. So we take 1, from multiplying all the numbers in the middle, we'll multiply it by this 1, which we'll put right here. We'll multiply by this 12. And note that 12 is congruent to negative 1 mod p, for it is 1 less than 13. So this is congruent to negative 1 mod p. Therefore, in this specific case, 13 factorial, or rather, not 13 factorial, specifically we have 12 factorial, that is congruent to negative 1 mod p. Note that the same exact process can be repeated for all numbers, since we showed that each number has its own unique inverse, mod p. And therefore, we have proved Wilson's theorem. We have p minus 1 factorial is congruent to negative 1 mod p. Cool, right? So now, we can apply Wilson's theorem to this problem right here. It states that an increasing infinite arithmetic sequence of positive integers contains 17 factorial and 18 factorial. Find the greatest x just such that x factorial is contained 2. Note that we're saying that x is an integer, although we didn't specifically specify this. We'll say that x is an integer. So now, let's figure what this is. For simplicity, we can let our arithmetic sequence be 17 factorial, 18 factorial, ... such that so that we know that we can contain every necessary element that must be in any arithmetic sequence. Because there's lots of arithmetic sequences that contain 17 factorial and 18 factorial, but since we want to find the x factorial that's in all of these, we'll just let it be the simplest one. 17 factorial, comma 18 factorial, comma ... right? And so, let's figure out what this sequence is. We can factor out 17 factorial, take a 17 factorial times 1, comma 17 factorial. Note that 18 factorial is 17 factorial times 18, ... And note that 17 factorial, this is also equal to 17 factorial times 17 plus 1. And since this is an arithmetic sequence, we can deduce that the next terms will be 17 factorial times 2 times 17 plus 1, and then 17 factorial times 3 times 17 plus 1, and so on. So, what integers does the sequence contain? We can see that it contains all numbers of the form 17 factorial times 17a plus 1, where a is an integer. It's an integer. And note that this right-hand side, the other thing we're multiplying it by, that is just 1 mod 17. This is, by definition, 1 mod 17. It's 1 more than a multiple of 17, right? And so, we know that our sequence will contain all numbers, whoops, I can't spell numbers of the form 17 factorial times 17a plus 1. And so for now we can factor out 17 factorial. And so we want to find the largest x such that x factorial equals 17 factorial times 17a plus 1. Note that this right here is not a multiple of 17. and this right here is a multiple of 17, but if you list it out, it's not a multiple of 17 squared. It only has one factor of 17, if that makes sense. So we know that therefore this must have one factor of 17. In other words, 17 divides it, but 17 squared does not divide it. Note that if x is greater than or equal to 34, x factorial will be something ... times 17 times ... times 34 times ... and therefore 17 squared would divide this, which we know is not possible. Therefore, we know that x must be less than 34. So what happens if, for example, x equals 33? Then we want to find if 33 factorial is equal to 17 factorial times 17a plus 1. Well, we can divide both sides by 17 factorial to get 18 factorial times 19 factorial times ... times 33 factorial is equal to 17a plus 1. So we want this right here to be congruent to 1 mod 17, because this right here is congruent to 1 mod 17. So we want to do mod 17 of the left side. Oh, I just realized there should not be factorials here. I'll rewrite this. It should just be 18 times 19 times 33, all the way to 33. So 18 times 19 times ... times 33. No factorials, right? And we want this to go to 1 mod 17. So we can rewrite this as 1 plus 17 times 2 plus 17 times ... times 16. Sorry, 16 plus 17, right? And we take mod 17, and this is equal to 1 times 2 times ... times 16 mod 17. But note, this looks familiar, right? This right here is simply equal to 16 factorial mod 17. And we know that this is equal to 17 minus 1 factorial mod 17. And by Wilson's theorem, this is finally we're going to use Wilson's theorem, we know that 17 minus 1 factorial is congruent to negative 1 mod 17, right? Which means that we have that 33 factorial is congruent to negative 1 mod 17. Well, actually, we forgot that we divided by 17 factorial, right? So 33 factorial over 17 factorial is congruent to 1 mod 17, which means that 33 factorial is equal to 17 factorial times 17a minus 1. We don't want minus 1, we want plus 1, right? And so, how do we change this form? Well, note that 33 is congruent to negative 1 mod 17. So 33 factorial is equal to 32 factorial times 33, which is congruent to 32 factorial times negative 1 mod 17, right? Because 33 is negative 1 mod 17. And since we know that 33 factorial over 17 factorial is congruent to negative 1 mod 17, we know that 32 factorial over 17 factorial times 33 is congruent to negative 1 mod 17. And so therefore 32 factorial over 17 factorial times negative 1, since 33 is congruent to negative 1, is congruent to negative 1 mod 17. So therefore 32 factorial over 17 factorial is congruent to 1 mod 17 if we just divide both sides by negative 1, right? Cancel out the negative 1s. So we know that 32 factorial over 17 factorial is congruent to 1 mod 17, meaning that 32 factorial over 17 factorial is equal to 17a plus 1 for some integer a, and we have a 32 factorial equals 17 factorial times 17a plus 1. This is exactly the form we wanted, right? If we scroll back up, we can see that our sequence contains all terms of this form right here. Wait, sorry, not that form. It contains all numbers of this form right here. This is what we want. So, we note that this is exactly what we found. 32 factorial is of this form. Since we know that 33 does not work, and anything greater than or equal to 34 also does not work, for the reason that now 17 squared divides that, we have that our answer is 32. And we're done. Thank you for listening, guys, and I hope you see another video.